is by Igor Sokolov. Igor Sokolov is a native of the former Soviet Union, as more or less the name says. So he studied in present Russia. He studied in Moscow State University, and then has, after in physics in the Moscow State University, and then since then he has been making very many research stays and that since the fall of the wall in Germany, first in Freiburg in Breisgau, first in Bayreuth, then Freiburg in Breisgau, and then since
2001.
Since 2001 in Berlin, where he's now professor of, I think, this nonlinear dynamic and statistical physics. So
yes, it's a chair for statistical physics
and
nonlinear dynamics.
Where he works in the same department as Lutz Szymanski.
Correct, we're neighbors.
You know. So, and his main research topics beyond the one that will be the subject of the talk today, anomalous diffusion. He's also working on temporal networks, so if anyone is interested. And then this topic also has some side connection with biology, as you will see this crowd environment, so he's also interacting with biology. So thank you.
Thank you for this nice introduction. And let me start. So first, don't look at this house. I don't know what it is. It's something the PDF maker puts there. I have no idea. This is our main building. This window is the window of the room where Max Planck used to work. So it's a nice old university, but we are sitting far outside on the other side of nowhere. And essentially what I will be speaking about in a very simple manner is mirrored in this short review which I have written a year ago. So almost everything except for the newer parts, which I will also try to show at the end of the talk. It's a relatively critical article, so if you are interested, just have a look. So let me start from diffusion. Yes? It's soft matter. Yes. It's soft matter 2012. If you want, I can give you the full reference, but this is the DOE here. Okay. If we are speaking about diffusion, we have to start with Adolf Fick. This is Mr. Fick. Think this away. Again, I don't know what it is. He needed the diffusion equation essentially for a biological purpose. He was neither physicist nor chemist, but a medical doctor with 2 years mathematical education. He started maths, and then his older brother told him, leave this stupid stuff, and this was around 1830. Become a doctor with your analytical skills, you will be a great doctor. And this is exactly what she did. And his older brother was a great lawyer. He was practically the first physiologist and had the corresponding chairs in Zurich and then in Würzburg in Germany. And he needed something for transport of nutrients through the membranes. And he started from the continuity equation and from linear response equation, from what we now call linear response equation, but this he called Ohm's law of diffusion. Ohm's law was already there, and the heat equation by Fourier was already there, so he simply followed the pattern, and then he put both ingredients together and put down the diffusion equation. He already believed in molecules, which was not widespread in the time, so he had a clear molecular picture behind it. Not clear on our scales, but on that stage of argumentation. And he solved this equation for cylindrical geometry, for spherical geometry, so he knew what's going on. The equation itself was not understood until Einstein, and Einstein essentially went somewhere else, but he derived the equation. This was the work 1905, and he started postulating that what Fick thought to be concentration is proportional to the probability, or probability density, to find the particle somewhere. And then he starts with the following postulates. First, there exists some time interval tau, so that the particle's motion during two subsequent time intervals is independent. We, in what follows, we would not need independence, but we need the fact that the corresponding things are non-correlated, which follows from independence. Then he assumed that the displacement during the subsequent tau intervals are identically distributed, which means that the corresponding increments follow a stationary random process. Again, we will not need the identical distribution. We only will need a weaker thing, a stationarity. Then he considered unbiased diffusion first, in which case the increments were symmetric. I will leave them being symmetric. But he also considered the bias situation, because he needed it. From this, the famous Einstein relation came. And he assumed that the second moment of the displacement does exist. Here I will stay, at least for a while. And essentially, with these requirements, he formulated something which is a random walk model of diffusion. He was not the only one, and the name doesn't stem from him. The name stems from the same year, from a question to the readers of Nature put by Carl Pearson, who was working for British colonial ministry and was interested in infection spread. Essentially, he was interested in the mosquito spread. It was clear that malaria was transported by mosquitoes. It was not clear until around 1920 what kind of mosquitoes. But he put a question to the readers of Nature: who of your readers can find a solution to the following problem? A man starts at point 0 and makes L yards in whatever direction, then he changes his mind, makes another L yard in a different direction, and required is his position after n such stretches. In a couple of weeks, Lord Rayleigh responded and told the problem was solved. The problem was solved in 1980 in his work of addition of summation of oscillations of the same pitch and random phases. He needed this for the theory of sound to answer a question: why do 10 violins sound 10 times louder than one violin, and not 100 times louder? Because the intensity is proportional to the amplitude squared. The method he used is based on what we now call the Pauli master equation. So he was the inventor of the master equation, essentially. And there was another work on random walks, a real mathematical breakthrough in 1900. This was the thesis of Bachelier on the theory of financial speculation, where essentially the same model was followed. So this is a little bit of history, and now we go on. And essentially, the random walk model puts the motion as a sum of small increments. The current position of the particle is the sum of these steps. If the mean squared step length does exist, and if the mean relaxation time, or the typical time of the step, does exist, then the mean squared displacement, which is this sum squared. Now I open the square, and this is what I get. I average over all different realizations of the random walks, and I single out the diagonal terms in this sum. And I get n times mean value of s squared plus 2 times n times the correlation function. And this correlation function is a way because the increments are symmetric and non-correlated. And this guy is proportional to t divided by tau as long as tau is finite. So, and here the stationarity stays, essentially. The number of steps is the time divided by the typical time necessary to make the step. And this is then proportional to t to the power of 1, which of course also follows from the solution of the diffusion equation for the delta-like initial temperature. If I go a little bit into thermodynamics, this is essentially what Einstein also did. then I see that the stationarity of increments has to do with the equilibrium state of the base, of the bath, because the bath does not change, and therefore the properties of increments at different times are always the same. So this stationarity of increments is thermodynamically important thing there. I can do the same in the continuous picture, and this is essentially what Taylor did in 1922, and this is Taylor, Kubo, or Kubo-Greenberg, or whatever. Essentially everything is in the work of Taylor, and then I see the same, and I can connect the diffusion coefficient with the corresponding integral of the velocity correlation function, and velocity is essentially a limit of the increment of the corresponding process when I consider lag time to be smaller. Now, the more people looked into details of diffusion, the more people have found something which looks like a random walk picture, but does not lead to normal diffusion at all, because one of the postulates or several postulates are violated. So in this case, one gets the mean squared displacement going as t to the power of alpha, and this alpha is no more equal to unity. This was observed in animal motion, and this is a false albatross. When we were writing this feature article, we didn't see the picture. We only have seen in the Galley proof something where it was written albatross from archive. And as our friend biologist told us afterwards, this is a false albatross. This is not this wandering albatross which presumably makes the Levy works. It's a different kind. So you can distinguish between the super diffusion with alpha larger than 1, and you can distinguish and subdiffusion with alpha smaller than 1. And I will mostly speak about subdiffusion because I am going into crowded environments, into the very complex environments of cells, or very complexly built natural membranes or artificial membranes. And typically, if you don't have active transport there, if you look at something which is passively moving, due to this crowding, it's moving either diffusively or slower than diffusion. I only have 2 experimental pictures here because I'm going into the theory then. One of them, this was one of the older works, but an important one, where people have looked at naturally occurring lipid granula in the cell and have seen that the motion is subdiffusive. And there are huge fluctuations. These are different realizations of experiment. There are huge fluctuations, huge differences between different realizations. The differences are in the prefactal. The behavior is more or less the same. And another one is with some kind of ion channels on the cell membrane. I take these pictures because the group around Igor used some of our methods in proceeding the data, and we are in collaboration. Slowly, in collaboration with this. So essentially, by now there is a huge amount of experimental material. There are very different experiments. Essentially, any techniques which you use to track diffusion can also track the anomalous diffusion. So either you do it like Fick and you look at the mass transfer or current or polarization if you have the conducting media. You can look at fluorescence recovery after photobleaching when you bleach a region in a system, so you remove the particles there, and then you look at how the particles are diffusing into the empty region. So it's also the ensemble variant because you simply measure the total fluorescence here, the total number of particles. You can look at single particles, and here you can also do it in different ways. You can look at single particles like Perrin did it in starting from 1908 with Paty. He was looking in the microscope and simply marked the positions of the Brownian particles and then looked at their diffusive properties. Now one can look at single molecules, and one indeed looks at single molecules, or let's say at single ion channels here. This is a realistic single particle trajectory, and particle is a microscopic object here. Experimentally, it's hard, and experimentally, for example, if you get here, these are all trajectories they have. You can get only few in reasonable time, because really tracking a molecule is a hard stuff. Now, you can look at specifically at first passage times, either when two particles come together and something happens, energy transport, electron transport, whatever. Or you can look at the single particle sojourn time in a domain. The particle is here, you see the light, the particle is outside, you don't see the light, and you do the fluorescence correlation spectroscopy, and this is again a single particle. Now, so you have experiments which hint onto anomalous diffusion, and then essentially you can proceed in different ways, and different people proceed in different ways, and the experimentalists and mathematicians, on different reasons, start from a mathematical model of the process. So you see something, you say, okay, it's not diffusion, let's fit it, an experimentalist say. Fitting means that you have a mathematical model of a process, and you simply try to find parameters of this mathematical model. In the best case, you make a statistical test to check whether the models fits at all. We want to go a bit further and to discuss the physical model of the system which generates the process. Because the process by itself is relatively uninteresting. The question is, what can you say about your system? What can you say about, let's say, the cell environment if you are looking at a single particle being there? And then from the physical model of the system, we go to the mathematical model of this process, to the mathematical model of other processes. Because if you know what's going on, you can ask, and what happens if two particles react? Or what happens if it's an enzyme, what happens if this enzyme finds its substrate? And then you make your experimentally relevant prediction, and then you go back to experiment. So you need statistical tests from mathematical side, or from my side if you want. And you need the instruments for the mathematical description here and here if you want to predict. So what are typical physical models for the crowded environments? And typically you say, okay, it's look like this, it's probably this, and you borrow models from other domains of physics, unless you are really able to look inside the system. One of the oldest models of anomalous diffusion was the trapping model, or energetic disorder, starting from different variants of random potential models. This is something which was formulated as early as 1975 for xerographic media, for strongly disordered or simply dirty or glassy semiconductors. Then there are trapping models of geometric nature. You again have a particle which diffuses, bombs gets trapped, but now you get trapped like on a comb, you get trapped in the side, so to say, in a tooth of this comb. You cannot move on the main, in the main system. The transport is hindered. And these combs do really exist. For example, if you have the dendrites of neurons, you have spikes there, and particle going into a spike does not move along the axis. So the model is quite realistic, and this kind of transport models are relatively simple. And mathematically, they are described by continuous time analytics. I will talk about what it can. Then another model, approximately as old, is the diffusion on a fractal structure. And in the labyrinth, the famous Degen's work from, I don't remember, early 70s. Again, partly from polymer physics, partly from disordered semiconductors, again. Here one typically speaks about structural disorder, because you have geometrical structures which are very complicated. or labyrinthine environment. This word labyrinthine environment stems from Katja Lindenberg. She needed to describe what it is. She invented the word, but it's exactly what it is. If you come into the labyrinth, you are slow. You cannot traverse it immediately. And then there is another class of models, which at the first glance is very different, but also known since almost minus infinity, namely 53. This is what happens. This is what happens if your particle is a part of a complex viscoelastic system. For example, if you are looking at a single monomer on a polymer molecule, the motion is strongly hindered by the fact that only collective motions are allowed. You alone can only move one step here and one step there until your neighbors moves. The system has very slow dynamics here. If you can describe it within the linear models, they possess slow modes. And again, the situations here are quite different. This situation is essentially not as different from this one as it might seem. This is a multi-particle or multi-dimensional variant of this. I will show it only on one slide because one gets inside and then one asks, what do I do with this inside? But essentially, all these models are variants of hidden Markov models. Whatever you can simulate with Monte Carlo is a hidden Markov model. Everything here can be simulated with Monte Carlo. It's a hidden Markov model. You have Markov dynamics, because Monte Carlo cannot do anything except for Markov dynamics. But you are looking at a very awkward variable, which by itself does not make a Markov process. It's either a projection or something very collective or whatever it is. So there are theorems, but as many mathematical theorems, they don't give any guidance for what to do in each particular case. And this is essentially what we need. So we need instrument for particular models, and some of these particular models comes with very beautiful instruments. For example, the CTRW comes with a fractional Fokker-Planck equation. This is a fractional derivative. In this case, Riemann-Liouville 1, a beautiful integral differential operator which shares many properties with the normal differentiation operator. So you can solve the equation, therefore you love the equation, especially as a mathematician. You can put the boundary conditions, you can put the initial condition, you can solve the equation. The question is whether you know that the model applies to your system, because you can solve the equation which doesn't describe anything. For fractals, essentially, the only thing you can do is you simulate. You can put down some equations about which you know from the very beginning they are approximate. For viscoelastic models, if they are linear, you can push the generalized Langevin equations. As always with Langevin equations, if you cannot make them to Fokker-Planck, you cannot solve them explicitly, except for very special cases, which are simple, free diffusion. But at least you can say something, or you can simulate them. You can find the solution numerically. And then what experimentalists very often do is they say, if I see the anomalous diffusion, let me fit my data with time-dependent diffusion coefficient. So I have not a very large amount of data, because the experiments are typically very hard to perform. You have error bars, which looks like this, and then you fit, and this is wonderful. So again, you get some insight into it, but you don't know whether it applies, and the equation is very simple. It's the Fick's equation, where this is diffusion coefficient, and you put here the explicit time dependent. As we will see, this guy is a relative of this guy. It's to no extent, for example, this is Gaussian model. This is to no extent the relative of this guy, for which it's often mistaken. You can derive this guy as an equation for this, but as soon as you try to use it, you will see it doesn't work. And then the question is, what's derivation? It's an equation for one point PDF, but it's the same as to say it's Gaussian and it's go like this with time. Okay. let me start from where it started, namely with disordered semiconductors, with zero-graphic media. You have here this disordered semiconductor. You have a semi-transparent electrode there. You create the charge carriers with a light flash, and then they have charge carriers of one sign. Will have to go from here to here, and you measure the current. And in the normal case of normal diffusion or of ohmic conductor, you will see here, this is double logarithmic scale, an error function as a current. You can immediately get it if you look at the diffusion, and if you remember that current is the time derivative of polarization. Polarization is the dipole moment of your system, which means charge times number of particles times the mean particles position. And then this is exactly what you get.
Sorry, is this a function of what?
Sorry.
It's a function of what? Of time?
This is time, yes, t divided by some characteristic time, and this is the current, again normalized correctly. And here you have the same. And this is from Scher and Montrell's world. And this was non-organic, this was organic semiconductor. It doesn't matter. If it's strongly disordered, it's always the same. And what was interesting is that the sum of the slopes of the initial and terminal part is always 2. I will not speak about the terminal part, but this is how they came then to the theory. And the model was the following. So you have threads there, you have strong irregularities. Essentially, these are the density fluctuations of the dopants. And here you have, in the density of states of your semiconductor, you have an exponential tail which protrudes into the energy gap of a crystalline one. The states here are strongly localized. So what you see is essentially the thermal activation with, according to the Arrhenius law, and this is the density of states. So you are sitting in one of this localized state. You wait until you are activated, you make a jump, and then you get trapped again. So this is the multiple trapping model, and the times of sitting you can get from these two, from this probability distribution and the dependence of the waiting time on the corresponding energy, and you get that it is a power law. The distribution of waiting time between the two jumps follows a power law, and this power -1 minus alpha. Alpha depends on the temperature and on the disorder. So you have to have enough these localized states in your system. The lower the temperature, the smaller the alpha, and if alpha goes below unity, this guy loses the first moment. So you violate the, so to say, second or first Einstein's postulate. If it loses the slow moment, the mean waiting time diverges, and you automatically go into this non-stationary class of the random processes. I wouldn't go now into mathematical details because I want somewhere else, but this is where you go. Then the mean number of steps doesn't go as t divided by tau, but it's governed by this exponent alpha. It goes as t to the power of alpha. The rate of steps decays. And the mean squared displacement, which is still proportional to the mean number of steps, goes as t to the power of alpha as well. And now alpha is smaller than unity. So this is the first mechanism of subdiffusion which was ever discovered. And this has a very nice mathematical picture, which is older than corresponding physics and stems from financial mathematics. It stems from mathematics, okay, Bochner's subordination, 53, I think, and then from financial mathematics, was used in finance, and then now it's used here. So what you say is the following. You perform a normal random walk, but what you do is you have your own clock, which gives you operational time. This is, for example, the number of steps, and this clock goes very irregularly on the physical time, and this clock is on the average on delay. So this is how you get from the normal diffusion, the anomalous one, and the probability distributions of positions at any time is simply a weighted sum of the probability distributions after n steps, weighted with the probability to make exactly n steps up to the time t. N is the operational time, t is the clock time. This in the theory of subordinated processes is called the parent process, and this guy is called the leading process. And the terminology is that the process you see is subordinated, in my case, to the Gaussian, to the parent process, under the operational time which is given by the leading process. Percolation, let me go to the next model. In many cases, you really see something related to percolation. This is a percolation cluster. This is essentially a pseudo experiment which people did. And the percolation, in percolation, you violate another postulate. Your increments, your steps, are not identically distributed, because in this case, for example, you have 1, 2, 3 neighbors. In this case, you have 2 neighbors, and you cannot go here. And again, what you see is anomalous diffusion. Polymers. What you see here is a Rouse model. It's a very simple bead and spring model. This all is in honey, in a viscous fluid. And if you look at the end-to-end distance, for example, but also practically the same happens if you look at any bead position, as long as you do not diffuse on the whole size of the molecule, you see anomalous diffusion here with slope 1/2, but making here a couple of side chains, you can change the slope. So you see subdiffusion. Instead of 1, you see 1/2, and then it's saturated. It saturates because it's the end-to-end distance. The ends cannot separate more than by the length of the molecule. And if you look at a single monomer, on the contrary, it will go to normal diffusion because the whole will diffuse as a whole thing. It has many close relatives. For example, the single file diffusion. Just a second. Okay, I will show it a bit later. And this is a non-Markovian process with stationary increments, but the increments are now not uncorrelated. They are correlated because you have the memory elongation. So, the intermediate conclusions. Anomalous is normal. There are many models there are many systems and many models which show anomalous diffusion. Second is from Lev Tolstoy. It's in the beginning of Anna Karenina. Happy families are all alike. Every unhappy family is unhappy on its own way. You have many models that are very different. If you start doing mathematics for them, trying, for example, to describe a chemical reaction, the mathematics is different and the reaction kinetics is very different. And all these models, introduce or imply a kind of memory. It's either memory of the simplest way, I'm sitting here and I have a memory when I came, or it's a memory about the increments. So now the two things which I announced, one was about the scale Brownian motion or diffusion coefficient which depends on the time. Start with continuous time random walks. There are many continuous time random walks trajectories, and do what is called pooling in the theory of point processes. You put all of them together, and then you can prove, people prove, the following theorem. The process, this is the leading process, the pooled process tends to a Poissonian process with the corresponding kernel which decays with time. And if you look at the mean squared displacement under this, it is a Gaussian mean squared displacement exactly distributed by this. Physical interpretation, if you have many continuous time random walkers and you look at the center of mass of the cloud, this is exactly the equation which describes the center of mass. So it's mean field for CTRW. It's not mean field for fractional Brownian motion or something else. Now about Rouse. This is a one-dimensional polymer chain. And now just represent a motion as a king flip. This is the Orwell-Stockmeyer model, one of the simplest model which you can use to numerically simulate the motion of the polymer chain. Now, say the following. At any place the chain goes down, I have an empty place, and at any place the chain goes up, I have a particle. Or I start with a single file diffusion. This is now a tube. I have particles in the tube. And then wherever there is a particle in the corresponding position or in the corresponding compartment, I draw a segment up. I can draw a spin up if you want, but I draw a segment up, diagonally. And then the models are equivalent. If I take only one king to jump, I get the random walk on a random walk or Kerr-Kuttner model, which is exactly solvable. This is the only case where the model with range disorder is simpler than a model with a nil disorder. But the models are the same. And now if I look into the state space of a single file diffusion, I took it 5 sides, 2 particles, 3 holes, because the total state space is then a planar graph. But you can reproduce the state space on computer, and you see what the model does is normal diffusion on a fractal projected onto the Euclidean space. The Gaussian part stems from projection. The anomaly stems from the configuration. So we have many models with very complicated relations between them, but there are essentially 2 classes. And now I will speak about these 2 classes. So back to the basics. Normal diffusion was a process with symmetric, stationary, non-correlated increments. I will stay with symmetric, but let's have a look stationary, non-correlated. And let me look at position correlation function. This mean value of positions at 2 different times. Why I am interested in this? I am interested in this because, knowing this, I can calculate the displacement, or the mean squared displacement, between 2 instants of time. So I prepared my system somewhere. Now at time s, I make my first measurement. I localize the particle. It's a classical particle. I can localize it. And at time t, I make the second measurement. And then I average the displacement squared. And this is what I get. So if I know this for all t and s, then I of course know this, and I get this. And this is something interesting because I can measure. Now if I have anomalous diffusion in which this guy behaves as t to the power of alpha, according to my measurement, and if I assume that my process has stationary increments, which means that x of t minus x of s squared is this, then I immediately see that whenever the process starts, I can shift the time here. This guy is this guy. There is no possibility to say where it started. If the increments are stationary, there is no possibility to say where it started. It doesn't possess an age. It does not age. If your system, if your bath, because the particle is not an equilibrium. A particle cannot be an equilibrium. It's not a thermodynamical ensemble. Only the ensemble of particles can be in equilibrium. But if the bath is in equilibrium, nothing changed in the course of the time, nothing ages, your system is stationary, your process is stationary. And the most important process here is you simply assume that this is given by this, because it's the simplest assumption. You simply take this formula and put this formula here, here, and here. And then this is fractional Brownian motion if you additionally assume Gaussianity, as you can do it for simplicity. So the Gaussian model for a stationary, for a process with a stationary increment is the fractional Brownian motion of Mandelbrot and Van Ness, or of Kolmogorov, invented for that. Now let's look at non-correlated increments, which will be, as we will see, not stationary automatically if your diffusion is not a normal diffusion. So let's have a look at this correlation function. And let me split this interval from 0 to t into the interval from 0 to s and to the interval from s to t. If your increments at different times are non-correlated, then this guy is 0. They are symmetric and they are non-correlated. This guy disappears. So this correlator is equal to the correlator at the earlier time. It's x squared to s. Now put this guy into this formula, into my formula, and you get that the mean squared displacement between s and t is equal to mean squared displacement at t minus mean squared displacement at s. This is almost trivial. For anomalous diffusion, I get then this, and I get from this guy. Now, if I look at the process which started at some t0, I see that by fitting at 2 subsequent points, I can get this t0 as long as alpha is not 1, as long as diffusion is not normal, and the guys cancel. So this means that for such processes, by a 2-point measurement, I can get the age of the system at the beginning of the experiment. The system does possess the age, and the system ages. Now, CTRW is essentially the process of this time. To see this, it's sufficient to resample it. Now, I look at it as fixed time increment process, and I look at the increments at different delta t, let's say. If I have a step, then I have here either a step to the right or a step to the left, but this was a normal walk, normal random walk with uncorrelated increments. They were uncorrelated, they stay uncorrelated. However, they are not independent, because if there is a non-zero increment and a longer interval, the higher the probability that the next increment will be 0. This is the memory in the system. Because if I return back here and look at it from the point of view of James, so to say, I would say, okay, if I didn't move, presumably I am in a deep trap. And if I am in a deep trap, then presumably I wouldn't move. So the process has this kind of memory, which comes into the fact that the increments are not stationary. So here I have now all these possible, not all these possible, but all these typical popular models. I have trapping as described by continuous time random walks. It's uncorrelated model. It does age. This I will talk about just now, and it's a non-Gaussian one. If you plot the PDF, it's non-Gaussian. Whether it helps or not, it's a different question, or whether it matters, or whether you can see that it's not Gaussian. If you, here you can. Okay. If you look at percolation, you see that you have correlation. You simulate, you see the correlations there between different steps. It doesn't age, which means it's an equilibrium model. And it's not Gaussian if you plot the PDF. If you have a huge realization, or many realizations, you plot the PDF, you see it as a custom. Tails which decay slower than a Gaussian. This is this changing environment, scaled Brownian motion, diffusion coefficient depending on the time, uncorrelated. Aging, if you take the equation seriously, because the time is explicitly in the equation. And Gaussian. Well, I will speak about this in a second. And if you take the fractional Brownian motion, this polymeric model, whatever, it's anti-persistent, it's correlated, it's in equilibrium, and it's Gaussian as well. Now, what about moving time average? In many cases, when you have a single trajectory or only a few trajectories, you take the trajectory and try to get diffusion coefficient from the trajectory by applying the moving time average like this, essentially like this, integrating along the trajectory. In the case of normal diffusion, nothing interesting happens, and you get the same diffusion coefficient as you get from the ensemble measurements, because normal diffusion is ergodic. And ergodicity is hidden in many places in the definition, and I don't go into proofs. Now, if you, for example, go into CTRW, and this is the result for ensemble for CTRW, the first thing you see, I don't have a picture there, but I can go back to the experimental picture. You see something like this. Different trajectories give you different diffusion coefficients. This is the first thing you see. It's interesting, okay, you can predict the mean diffusion coefficient. Sorry, I removed the picture from the proper place, but let me stay here. Let's average over many trajectories. Let's get the mean. We get the mean by applying ensemble average to the time average. We can exchange the averages. We can then take the integral of this guy. This is the ensemble average, and we take the time average. And what we get, it goes proportional to t. You see normal diffusion on the average. So we know that you have a model which in the ensemble mean gives you anomalous diffusion, but in the time average, you see scattered, so to say, normal diffusion. And you can use it, the diffusion coefficient depends on the observation time, and the diffusion coefficient, if it were diffusion, dies out. Alpha is smaller than 1. So what you see is normal diffusion, but with diffusion coefficient depending on how long your trajectory is, and the longer it is, the closer is the diffusion coefficient to 0. And you can use it as a test for distinguishing the models. These are the model experiments, essentially, and you can distinguish by this something which has traps from something which does not have traps. In the traps, you see an ensemble anomaly. In the time average or double average, you see the normal diffusion. Here, in percolation, you always see anomalous diffusion, and percolation is also ergodic. You see the same whether you take a single trajectory, many trajectories, whatever. Although you see very strong fluctuations, which means that the convergence is extremely slow. For SBM, which is a mean field for this, again, you see normal diffusion in an anomalous model. And for viscoelastic, it's always anomalous. Now, let me probably go. You can do the same on single trajectory levels. You need different tests. This is true, but you can distinguish between these classes. And now maybe, do I have 10 minutes, or it's better to guess? And then I will go into one very simple thing. It's a generic random potential model, which can be both the traps and the percolation. And essentially, this is a generic model if you do then projection underlying whatever. And the question is, when do you see anomalous diffusion, and what kind of behavior do you really see? So I will start with the master equation, going back to Rayleigh, essentially, but this is a modern form of it. I assume that my system does possess an equilibrium state, which means that if it's a cell, it can be dead. So equilibrium is death, this we know, but it does possess the dead state, which means that I have the detailed balance. And if I have the detailed balance, and this guy, I can make a trick. I will show a trick then, but I won't show the theorem level behind it. I can make a trick and project this on something which is almost like quantum mechanics. Because under this condition, the matrix of transition rates has exactly the same number of elements, or independent elements, as a Hermitian matrix. But essentially, I will do something a little bit different than putting it Hermitian as mathematicians do it, and then looking at the spectrum, because most of the properties here are non-spectral, which means that they change when you rotate. And then one can prove on the theorem level, and we were not alone who did it, that the mean diffusion coefficient is something when you take this transition rate weighted with the equilibrium probabilities and make the average in the sense as you will calculate the conductivity of a large disordered lattice with the conductances given by this guy. So this is the effective medium. It's not effective medium approximation. This is the conductivity in the corresponding effective conducting medium. And this is simply the mean Boltzmann. This, on the very physical level, this you can prove. This is mathematically, so to say, exact. If this guy exists, then this holds. And what I'm doing here, I am essentially on the physical level using this. I don't know what is this, that sigma is the concentration times the mobility, and the mobility is connected with the diffusion. And you do it close to equilibrium because the long-time diffusion coefficient is an equilibrium, is something you observe close to equilibrium. And this is then the diffusion coefficient, and this guy is the mean, proportional to the mean concentration. And what you see then is that this can go to 0. You can observe subdiffusion, either if this is 0 or this is infinite. Superdiffusion in this model is impossible, but this is a model for subdiffusion. There is no active transport. Active transport will break a symmetry, which is assumed by the derivation there. And then either this diverges, and this is this energetic disorder, or this is 0, and this is structural disorder. And structural disorder you can see only in 1D or on the percolation transition. Again, you can prove it on the theorem level. So you have either percolation, if you are not in 1D, or this something which is CTRW-like. However, you can have both for the corresponding distribution of the elements, and this makes it very complicated because you can have subdiffusion of mixed origin. At the same time, if this guy diverges, this is essentially, if you put here the sum divided by 1 over n, the sum is the partition function of your system. This means that the partition function diverges on the on the lower bound. This means that you violate the third law. So your system is not thermodynamical system in some sense. In some sense it is, in some sense it's not. It shows strong fluctuations, but these are strong differences between different realizations, strongly realization dependent. So you see huge fluctuations, which then might be interpreted either as inhomogeneity or as ergodicity. And the same happens on the percolation transition. You see fluctuations. So you have to be aware that the system homogenizes extremely slowly if you do an experiment. And both can happen simultaneously. Now, if you go, now I will be very, very short, and I will tell only the following thing. So if you go into the full derivation, this is how you can pose your system. This is a pencil of Hermitian matrices. This gives you the spectrum, and this gives you then the time composition. So you essentially, this guy defines the leading process, and this guy defines the parent process. And you can go here from here always whenever you have a true equilibrium. And then you can look at a moment, which is here. You can look for a moment which is additive. You say you take your trajectories and look for a moment which is additive in time. This additivity is inherited from the parent process. I will call it the fundamental model. And if you calculate it, you can do it in simulations. We didn't do it in experiments. This is quite fresh, as you see. Yes, 5th of July this year. You can get it. This is the model of generic random potential. This is 1D. You see that this fundamental model, this is for barrier model, when you have only different barriers. This is generic, this is simply a random potential. Random barriers, random energy wells. And you see this fundamental moment, which follows from barriers only, fully from the structural disorder. Because barriers in this model are projected on the structural part. Again, you can do everything clean. And the time dependence, which used to be of this fundamental moment, which used to be the first moment of the leading process, is fully inherited from the traps. So you can see both. This is very new. You can always separate between traps and structure. So here, maybe I finish, but I show only one small thing afterwards. So it's the following, that distinguishing between different classes is essentially simple, especially on ensemble level. You need it. The behaviors are different. One does age, another doesn't age. One can mimic normal diffusion, although being anomalous, another is always anomalous. So you have to be aware of all these pitfalls. But it's in principle possible as long as you have an ensemble. Now, it's very interesting what happens. It's again relatively new. It's very interesting what happens if you try to distinguish between percolation and FBM on a single trajectory level, if you have only one trajectory. And we have a computer, and we can generate the trajectories which are, let's say, infinitely long on the experimental scale. This trajectory is at least 100 times longer than what Goldman and Cox had in their experimental work. And look, red is percolation, blue is FBM. Red is percolation, blue is FBM. First tell me what's Gaussian here and what's non-Gaussian. Both have memory. In both cases, the self-averaging is very slow. Both processes are essentially ergodic. Mathematically speaking, there will be a self-averaging, but not on the experimentally relevant time scales. You can still distinguish, if you look at the correlation functions, it's very nice. In the initial models, they are the same, but we simulated a couple of others. Red is the